Hello everyone and welcome back. This is Mr. Brocklehurst here, and I am here only in video form today because, as you know, there is a substitute teacher here. So we're going to start out today by opening the document for NetForce. So please find that in Google Classroom. We'll pause the video here to give you time to do that. We'll be back in 1 minute and 30 seconds. So please find the document, check your neighbor to see if they need help locating it as well. Check back in a minute and a half. Okay, welcome back. So today you'll mostly be taking notes on NetForce on your own, but since I am absent today, you can refer to this video for guidance at various points. Each student is going to complete their own notes. You're going to use your group to talk through any confusing concepts and also to compare answers with. Today we'll have perfect groups. In a moment I'll flash the screen for your perfect groups. Please bear with me. Okay, your perfect groups are as such. Ethan is going to assemble his group over at stations 1 and 2, Phoebe at stations 3 and 4, Tommy stations 5 and 6, Samuel at stations 7 and 8, and Ichien at stations 9 and 10. So please head there now. We'll resume the video in 1 minute. Okay, and welcome back. So, as I mentioned, today you'll be working on this worksheet for NetForce. I'd like you to take the first 5 minutes to complete the foursquare that you see at the top of the page for NetForce. Please don't peek at the answer or fast forward. It is far more important that you think through the definition than having you copy it down. So in this unit, you won't be assessed as much on memorizing as you will be on understanding and applying. So make sure that you're thinking through this definition as you're going through it. Please talk it over with your group. That's why they're there. We'll come back in 5 minutes. Okay, so once again, please pause the video now. We will return in 5 minutes to go over the foursquare for NetForce. Do that now. Okay, and welcome back. Here's my particular response for the first foursquare. For definition, I have down that it is the combination of all forces acting on an object, and when we get more into that, we find out that there's more nuances to it than just combining forces. So it somewhat has to do with how or what direction these particular forces go. When the forces are in the same direction, we add, and when forces are in opposite directions, we subtract. We should know that when forces are balanced, that they end up canceling each other out, and we get a net force of 0. We should also know that unbalanced forces have a net force that is not equal to 0, which means they have not completely canceled each other out. When there is a net force, the net force is always a vector quantity, and that means it will always have a direction associated with it. We should also know that the net force will always have the same direction as the way the velocity is changing. It is not always the same as the velocity, but the way it is changing. Some non-examples are that you always add forces. That is not true. To find the net force, you only add forces when they are in the same direction. Another non-example is that you always subtract them. That is also not true. You only subtract forces when they are in opposite directions. Okay, and as you can see, I've made my own drawing for NetForce. I've shown that the push from one person and the pull from another end up being in the same direction, and so that's when I add those two forces to find the net force. 15 newtons plus 25 newtons does make 40 newtons. Okay, now that we've completed the foursquare, I'd like you to take the next 4 minutes and complete questions 1 through 4 as you see here. Please talk them over with your group. I will pause the video now and give you 4 minutes. Pause the video now. And welcome back. Okay, in number 1, if forces are balanced, then they would cancel each other out completely, meaning there's a net force of 0 essentially. But if they don't cancel each other out completely, meaning that there's a non-zero net force, then they would have to be unbalanced. There's still some force left over after all the balancing, so there's still a little bit unbalanced. Thus, the answer to number 1 should be A. And question number 2. Since the forces are in opposite directions, when we combine them, we have to subtract. The difference is 70 newtons, and it should be in the direction of the larger force, so it should be 70 newtons upwards. In question number 3, since the forces are in the same direction, when we combine them, we have to add. The sum is 1,500 newtons, and it should be in the direction of both forces, so it should be 1,500 newtons to the right. And then if we look closer at question number 4, we'll see that since the vertical forces are in opposite directions, vertical meaning up and down, when we combine them, they will cancel each other out. The 8,000 cancels out with the 8,000 going down. Okay. Since the horizontal forces, left or right, are in actually opposite directions as well, when we combine them, we subtract. The difference between 4,000 and 1,000 is 3,000 newtons. And it should be in the direction of the larger force. So it should be 3,000 newtons to the left. Remember, 8,000 canceled with the 8,000, and 1,000 of these canceled out with 1,000 of those, which leaves 3,000 newtons to the left over for our net force. Okay, now you're going to move on to part 2. You'll watch the video that is linked there, and then you'll answer question number 1 associated with that link. So, please pause the video now, watch that video, and come back in 4 minutes. See you then. Okay, welcome back. As you can see, here we are at part 2, question number 1. We've just watched the video talking about how many forces are acting on that particular dude at that particular time. And we see that not only is there gravity pulling it down, pulling him down or the ball down, there's also something called a normal force, or force from the floor, that is pushing back up. You know, just think of it this way: if there's only gravity pulling it down, wouldn't it be sinking down through the floor towards the center of the earth? So something must be keeping it there, and that is the normal force, or force from the floor pushing back up. And normal, once again, means perpendicular to the surface. So perpendicular to the floor means back up. Okay. Question B, describe the motion of the ball. Well, it's still, or it's stationary. Some people might say it's at rest. I would accept all 3 there. Okay, are the forces balanced or unbalanced on that ball? Well, the fact that it's at rest or stationary suggests that there must be no net force, and therefore it must be balanced forces. When there's no net force, it's always balanced. That means they've always balanced each other. They've balanced each other out. Okay, and letter D, what is the net force on the ball? Well, as we just said, there's no newtons, or there's no net force, so it'd be 0 newtons, and since there aren't any newtons, there's no direction either. Or you can say any direction. I guess you could say 0 newtons to the left or 0 newtons to the right, and both of them are the same, so I'd accept either. Okay, take a moment, get out your supplies. You're going to assemble the textbook ramp for number 2, and I'll join you in a moment. Okay, at this point, you and your group need to assemble the book, the wooden board, and also get the billiard ball placed at the top. You're going to roll the billiard ball down 1 time. You're going to observe very deeply what happened at point A, which is halfway down the board, and another point B, which is right in front of the ramp, so within the first 5 centimeters of the ramp. You can probably guess what it's going to do, but I'd like you to do it 1 time, observe as deeply as possible, because you're going to answer several questions about this in a moment. I'll pause the video here and let you do that, and then try to attempt to complete question number 2. Thank you. Okay, and welcome back. At this point, you should have run the experiment. You should have watched the ball roll down the ramp and then roll along the ground for some distance before coming to a stop by either hitting something or running out of energy. You should be able to answer the rest of the questions, A through E, and then start on part 3 and finish with the OLC quiz at the end. In any case, finish as much as you can during class. Whatever you do not finish becomes homework. And again, I do expect you to check your work at some point. Okay, you can always check your work against the key, which is always posted to the OLC. Of course, this is not news to you. It's been the same way since the beginning of the year. At this point, I'm going to switch to the key, and we're going to go over questions A, B, C, D, and E, all in that order. Okay, question A. What are the forces acting on the ball? Well, it's kind of complicated, but not too much. If we focus at point A, halfway down the ramp, well, there's going to be a gravitational force. That gravity always pulls down. There's going to be a normal force because it is in contact with an object, and that should be perpendicular out of the ramp. Okay? And since it's moving, there's going to be friction. And it's either going to be air friction or rolling friction or some other kind, but that should be up the ramp because it's always opposite the direction of the movement. So if it's moving down the ramp, then friction would be going back up the ramp. Okay? At point B, it's still moving right in front of the ramp. Okay, there's still gravity pulling it down. There's still a normal force. This time, perpendicular to the ground is straight up, so it's going up. And there's still going to be friction because it's moving. And if it's moving, that friction is going to go opposite the direction of its motion, so it would be to the left in this particular case. Okay. Part B, you're supposed to describe the motion of the ball. Well, and it's halfway down the ramp, it's still speeding up. It's still picking up speed, so you could say it's speeding up or accelerating down the ramp. Okay, at point B, just as it hits the bottom, I'll accept two answers. I'll accept that it's moving at constant speed, but I don't really believe that it is. If there's friction on it, and there should be, then it should be starting to slow down. It's moving to the right still, but it is starting to slow down. Okay, it's no longer gaining speed, it's starting to lose it. Okay, letter C. Are these forces balanced or unbalanced? Well, it's unbalanced in both cases, in truth, if you say friction is acting on the ball, and friction is acting on the ball. But let's go back to what we said in part B for point B. If you said it was at constant speed, I said I would accept that as an answer. Now, if you said that, then for part C, you should also say that the forces are balanced at point B. Okay. But if you didn't say it was at constant speed, if you said it was slowing down, then you should point out why it's slowing down. And the reason it's slowing down is because there is friction still on it, and that's the net force that's remaining. Okay, and the last one is part D. What direction is the net force on the ball? Well, in part A, the net force on the ball must be down the ramp because that's where its velocity is changing. It is being pulled down the ramp by something, and that must be the net force. At point B, the net force would be, well, if you said that it's balanced forces, then there wouldn't be any net force, so you'd say there's no direction. But if you do think that it is slowing down, then there must be a net force going to the left, slowing it down. It's like a pull. It's moving to the right, but something's pulling on it to the left so that it slows down. Okay? Hopefully that makes sense to you. If not, you can ask me more questions about it tomorrow, and we can do some more demonstrations. Okay, at this point, you should move on to part 3, answering many of those questions as you can. If you have not yet, pause the video now if you still need to work on question number 3. Oops, I forgot one. I forgot about part E. So here we are back at part E. While it's going down the ramp, remember normal force is perpendicular to the surface. So since the surface is slanted, perpendicular to it would be kind of outward like this. Friction would be opposite the motion. Since it's being pulled down the ramp, friction must be trying to resist that, so it's going back up the ramp. And remember, gravity is always straight down. Point B. Well, gravity is always straight down. Normal force is perpendicular to the surface, which is now horizontal, so perpendicular force must be straight up. And since it is still moving to the right, we're going to know that the friction is going to oppose that motion a little bit to the left, something like that. Okay, let's move on to part 3. So in number 3, part A, since the object is moving with constant speed and changing direction, then the direction of the net force must be to the right, since the writer is turning to the right. Something must be turning him. It must be a net force. Okay. Let's look at part B here. Part B. So this guy is gaining speed. He's started from rest and now he's moving. So his net force must be forwards or to the right, however you want to describe that. Okay. And we know that because he's gaining velocity to the right, and any change in velocity must be in the same direction as whatever the push or pull that's happening there. Part C. The object is moving with constant speed and constant direction. Well, that means its velocity is not changing at all. If there's no constant speed, if there's no change in velocity, then there is no net force. There's no direction to the net force, and it's basically the net force is 0 then. It must be balanced forces if he's moving at constant speed and constant direction. Okay, so far today, what you should have learned from this lesson is that net force is the combination of all forces on an object. Okay. You should also know that contact force is sometimes called normal force, and that's always perpendicular to the surface. Perpendicular, by the way, means 90 degrees, as you know. And then finally, velocity changes when there is a net force. Okay, it should change in the same direction as a net force. Okay, if you have not yet, you should take the OLC Forces Quiz 2 until you get them all correct. You'll find that once again on the OLC. Good luck, and I will see you tomorrow. Bye-bye.